Okay, so as we've noted in a previous video, we know the value of the call option using the Black Scholes model, and here we're going to solve an example that has some of the givens for this particular asset, and we're going to try to find the value of the call option. So if you recall, how does the call option look? The value of the call option is S0, which is the current stock price, times N of D1, which is the cumulative normal function evaluated at D1, minus E, the exercise price, divided by E to the RT. R is the riskless rate, T is the time to maturity, times N of D2, which is the cumulative normal evaluated at D2. So some of the issues that we have with the call with using Black Scholes model is trying to determine these factors. Okay, so usually these things are kind of easy to find. The S0, the current stock price, is easy to observe. The exercise price is basically observable as well. The time to maturity is easy to find. The riskless rate of interest is also easy to calculate. However, sometimes there's an issue with calculating the volatility of the stock. Okay, so there are methods presented in the textbook for how to go about doing that. I won't dive into too much detail, but it's just something to keep in mind that we would have to calculate the volatility of the stock in order to be able to use this formula. So as we saw in the valuation formula, we had an N of D1. Okay, so we need to evaluate the normal distribution at that value E1 to find the area under the curve. So in order to be able to know what D1 is, we first have to solve for D1 and D2, and then we're able to find the normal distribution values for them, and then we can plug them in and find the value of the call. Okay, so I rewrote the D1 formula. What is D1? It's the natural log of S0 over E plus R plus R times 1 up plus R plus 1/2 sigma squared times T divided by sigma times a square root of T. Okay, so let's plug in all these values that we have based on the numbers presented. Okay, so we have the natural log of 90 over 100 plus our R is 0.1 plus 1/2. Our sigma is 0.5, so 0.5 squared. Okay, and then the time to maturity is 0.5. Okay, because remember, we have to express 6 months in the form of a year, okay, as a fraction of the year. So T is equal to 0.5. So we're going to write that out. And the whole thing is divided by, sigma times the square root of T. Okay, so sigma is still 0.5. And square root of T is the square root of 0.5. Okay, and if you were to calculate that, you would end up with a value about 0.02. Okay, so just so you know, if you had a scientific calculator or a graphing calculator, this number, the natural log, there's a key for it called natural log, and you're able to calculate the value of the natural log pretty easily. All the other factors are basically regular calculations. Okay, so we've just estimated the value of D1. Now we have to do the same thing to estimate D2 and continue from there. Okay, so I wrote down the formula for D2. D2 is the same thing, except now we have, instead of R plus 1/2 sigma squared, now we have R minus 1/2 sigma squared. So we'll go ahead and write that out. It's equal to the natural log of 90 over 100 plus our R is still 0.1 minus 1/2 times 0.5 squared, and T is still 0.5 divided by 0.5 times the square root of 0.5. Okay, please excuse my handwriting. As you can tell, it's a lot harder to write on an iPad than on a board. So if we do those calculations, we get this value of minus 0.33. Okay. So basically we have to find out what's the value of the normal distribution at those two D1 and D2. So n of D1 is n at 0.02. N of D2 is n at minus 0.33. Okay, and if you had a normal distribution table, you'd basically be going down the left-hand side of the table to get to 0, and then up the top will be the second decimal place. So you'd go to 0.02, and it would give you the area under the curve to the left of that value. Okay, so if we were drawing a normal distribution, it would look something like this. This would be 0. So if you recall, about half the area of a normal distribution, exactly half of the area of a normal distribution lies up to 0. Okay, so the area up to this point, all this area here is 0.5. Now if you think about it, 0.02 is just a little bit to the right of 0.5. Okay, so our area will be a little bit over 50%, and so we'll see what that is. That's over there. This is the area that's a little bit greater than 50%. And if you did that, if you looked in the table for that value, you'd get 0.5080. Okay. Similarly, now minus 0.33 is to the left of 0, so the area will be somewhat less than 0.5. Okay, so we can estimate already. If we have a number for our D1 and D2, if we have a number that's greater than 0, we'll get an area that's a little bit above 0.5. If you have a number that's less than 0, we'd have an area that's less than 0.5. Okay, so if we find out the value for minus 0.33, you're going to end up with 0.3707. Okay, now we have all the components we need to be able to plug it into our actual value formula to find out what's the value of the call option at this point of time. Okay, so this is our formula for the call option. Okay, we have all the components we need. S0 is 90. Okay, N of D1 is here, 0.5080. Minus, okay, E is the exercise price, which is 100, divided by the exponent function, which is about 2.7, to the power 0.1 times 0.5, and then we multiply that by N of D2, okay, which is 0.3707. And if we did that calculation out, we're going to get a value of $10.46. Okay, so this call, if it's correctly priced, should be selling at $10.46. Okay, if the call was selling at $9.50, okay, let's think about it. If the call was selling in the market at $9.50, this call is undervalued in the market. Okay, the true value that we've found using this option is 10.46, but we're able to buy it for 9.5. Okay, that means the market is undervaluing this call option. It'll be profitable to buy it and take a profit of that. Okay. Now, some terms that are related to options based on what we've just calculated, okay, and in general. So, N of D1, that first term, this first term here in the Black Scholes model formula is called the hedge ratio. Okay, we had a value of 0.5080. What is the hedge ratio? It's the number of stocks you need to short for every call option that you purchased in order to obtain a riskless hedge. Okay, so those are the amount of stocks you're going to short in order to obtain a riskless hedge, in order to avoid any adverse effects of the stock price. Okay, so we had a value of 0.5080. that's a little bit above a half. So it says for every call purchased in the example that we just talked about, for every call purchased for the stock that was trading at 90 with an exercise price of 100, we would have to sell 0.5080 of the stock short in order to obtain a riskless hedge. Okay, so basically for every 2 call options, you'd short 1 stock, okay, approximately, because one stock is about half. One call option requires about half of a stock to be shorted. Now let's talk about a few of these things called option Greeks. Okay, there's a term given for that N of D1 term. There's a term given for the hedge ratio. The hedge ratio is called the delta. Okay, the delta. Now, the rate of change of the hedge ratio with respect to the change in price of the underlying asset, which means how quickly does that hedge ratio change with respect to what the true price of the stock is doing. Okay, the rate of change of the hedge ratio with respect to the change of the underlying asset's price is called gamma. Okay, so that letter is gamma. Now, the rate of change in the price of the option with respect to time, with respect to how much time is left to maturity, that value is called theta. Okay, and the rate of change of the option price with respect to the volatility of the underlying asset, which means how much standard deviation that underlying asset has, that is called vega. Okay, so we have 4 option Greeks. There's delta, there's gamma, there's theta, and there's vega.